This is design of okay. Now whenever we say that a n bit shifter is there, its objective is to shift the incoming data up to n minus 1 places. Okay, so if I say that I have a n bit shifter, what is the job, right? This is to shift the input data by, this is up to n minus 1 places. This is the first objective, right? Again, you have a second objective that you may require a left shift, or you may also opt for a right shift. This is the second objective. This is actually I have to specify how many positions and in what direction you want to shift. Okay, right. Now it is specified that the shift should be on an end around basis. Then any bit shifted out of the end data should be shifted back to the first. Correct? So there is what is called as uh, it's called as end around. End around. ENDAROUND. Okay, end around shift. There is another version of that. So normally whenever you shift a data goes out of your device. But when you say that I want to design an end around shift, the idea is that any bit shifted out at one end of the data word gets shifted in from the other side. Okay, so this means, let's say I have a data like this. Let's say I have 4 bits. This is 1100, right? So when you shift this data, let's say I am going to shift this data right by 1 unit. So what exactly happens if this is not an end around? So this one goes here, this one goes here, 0 comes here, and a 0 goes up. This 0 will never come back, right? You are going to shift the data zeros from the other side. Okay, zeros are 1 from the other side. But when I say that it is a end around shift, it's not like this. This means there is a connection. Always the connection of the shifter will be like this. This will go out and it will actually come from the other side. This is the end around shift. Okay, so in an end, if somebody opts for an end around shift, right, this means any bit that is shifted out at one end, okay, gets shifted in at the other end. Okay, again you should have an option whether you are performing the end around shift right or left. Okay, both are possible. Now let's say now our intention is to go for a 4-bit shifter, right? So if it is a 4-bit shift, correct, you have the easiest way to design, correct, that is, let's consider the number. Okay, I'll write a 4-bit shifter now. This is our requirement. How to design this we need to decide. Okay, this is a 4-bit shifter. Okay, now let me say that I have the number 1101. This is initial value that is stored in this. Okay, so in decimal, how much is this? What's the value of this number in decimal? Fine. So now let me assume that I want to make a shift. My shifting operation is in this way. So let's assume that I want to perform 1 bit left shift. Okay, and I want this to be end around. That means whatever moves out should come back. Correct? So what happens now? So see, you can see that as mentioned earlier, this is 1 bit left shift, right? Everything moved to the left, right? So I'll show you the marking. So this one comes here, this 0 goes here, because 1 bit shift to the left. What happens to this one, which actually goes out, right, from this side, because you are shifting, it will come from the other side and it will occupy this position. Are you okay? So the number which I'm writing now is 1011. Now, what is its binary equivalent? Sorry, what is the decimal equivalent? Yes, this is 11. Okay, 11, it's a decimal number. Then let's move to the same case. I want to perform a 3-bit right shift of the original data. Okay, again, I want this to be the end around, right? Okay, so we consider the same old initial values. It was 1101. Now, can you tell me the result? What happens when you shift that initial value to right by 3 bits? Yeah, okay. You get 1011. That's also 11, right? This is because there is what is called as a symmetricity, right? You are moving to right by some units is same as moving left by, right, n minus that unit, 4 minus 1 unit, that is 3 units. Okay, so moving left by 1 unit is same as moving right by 4 minus 1 unit, that is 3 units. Okay, because of that you have this kind of options that is coming out. All right. So in other words, moving a particular data to left by 2 units is same as moving the data to right by 2 units. Is it okay? Are you fine? Right. Okay. So we understood the basic concept what we have to design, right? When we want to design something, right? This is our requirement. Okay. Now, so what is the nature of the shifter you want? Let us say we have decided that I want to design a 4-bit shifter which performs this kind of operation. Right. Now we need to consider the requirements of implementation. Right. So shifting can be affected by loading the data at one end, because you see that shifter is present in our uh, processor, right? I had a processor design in which one of the block is called as the shifter, right? So this particular shifting, right, can be affected by loading the data, where at the output of the ALU. That is our main motor, right? In our circuit, the circuit of the processor which we are designing, right, the shifter is present after the ALU. So whatever changes at the output of ALU, the shifting gets affected because of that, right? Then there might be a requirement that you may have to read the data parallelly out, not serially. You may have an option to read the data parallel at each of the stage. So that is also a requirement now, right? Required the parallel output, right? Uh, for each stage of shifting. In the sense, my intention is to go for 3-bit shift, but I shift one by one, correct? So at every stage of shifting, I want to see what is the content of the shifter, right? So you need parallel output. Okay, so overall we can say that we have the following requirements of the shifter, right? So we'll write in short: requirements of the shifter. So point number one, it accepts input from a 4-line parallel data bus that is directly connected to the shifter. Okay, so it has to accept, it accepts input from where? From a 4-line, because it is 4-bit. Okay, 4-line parallel data bus. So data bus has 4 lines. Okay. Then the second requirement is that how many output lines you expect? Yeah. So it has 4 output lines for the shifted data. Okay, and there has to be a facility to transfer the input data to the output lines with any number of shifts, starting from 0 shift, no shift, to 3 shifts. Okay, so there has to be a facility for transferring the input data to the output lines with any specified shift from 0 to 3, because we know that if it is n bit shifter, you have the facility to shift from 0 to n minus 1. So it is 4 bit, so it is 0 to 3. Okay, right. So now we know that, right? What are the options you have? What are the various semiconductor devices you can use to build such circuits? We have options such as a transmission gate. We have an option to use the pass transistor, right? Again, you can use a crossbar switch, etc. These are the multiple options available, right? So our strategy should be something like, right, I have to have a full control of the direction of the data flow, and also I should be able to uh, move the data as I want, right? Provide a specific number of shift is what is required. Also should be able to control the left and right direction, right? So now we are going to see how you can use a 4 into 4 crossbar switch for this particular target. Okay, 4 into 4, this is a cross bar switch. Okay, now so let's give the input from one side and let's take the output from other side. All right, so this is the 1, 2, 4. Okay, I'm going to use these 4 lines as the output lines. Okay, then now in this diagram we need 4 input lines. Okay, so the input lines I'm going to draw, say like this. Sorry. Okay, say these are the input lines. 1, 2, 4. All right, now we build the transistors, right? Again, we are using NMOS pass transistors for this particular design. Okay, so the pass transistor should look like this. So if you remember the structure of a uh, pass transistor, this is how it looks like. Okay, let me draw a transistor with a different color so that it becomes easier for us to understand that there is a transistor. Okay, so and similarly, this is a line which goes like this, and this. You have a connection here. This is a gate. Okay, then the next transistor you build like this, and this is your connection. So like this, you design the in the same way the third line of transistors we are trying to build now. Okay, this. So each transistor is N type. Okay, now let's give the names to this. This is IN0, IN1, IN2 and IN3 input. Okay, similarly we have, this is out 0, this is out 1, this is out 2 and this is out 3. Okay, and you have for the select lines, right? There are control signals to be given, so we'll start like this. Okay, this is like SC00, the gate. Okay, whatever signal you pass to gate, we give a name to that. SC01, this is SC02 and SC03. Now here SC10, right? This is SC11, SC12, SC13. So here SC20, SC21, SC22, SC23, and the last set should be SC30, SC31, SC32, SC33. Okay, so I can see that we have a combination of select lines available so that you can perform the different required operations, right? The in lines carry the input data and the out lines will carry the output data, right? Now any input line can be connected to any output line or the all the output lines which has, right, something around our requirement. As per your requirement you can make these changes here. Okay, also if you see that all the switches are closed, all inputs get connected to all outputs, right? You can actually pass on the data, right? So this is what is the requirement here. In a sense, as soon as you give a signal, let me assume that, let me take one of the transistor to see what exactly is happening here. Okay, consider this transistor, right? And I pass a signal 1 here. This signal is high now on this line. Okay, this line is high now. The data 1 is present along the line IN3. Now what you are supposed to do, if you want to pass a specific signal, that is this high signal, one I want to pass to this line, this should carry 1 now. What do? You simply give input to this signal, this particular transistor, make the gate high. Means what? It will conduct, right? This transistor will conduct now. Conducts means this is available at this point, correct? And which means this point and this point are same. If one is available here, one comes here, that is what is my requirement. So now I'll ask you a question, right? Just to make sure that you are fine with this concept. Let me say, okay, this is my requirement. Just a second, I'll write it down here. Let me say I am passing the signals. My input signals are like this. Okay, my input signals along these lines are 1 0 1 1. Okay, and I want output to be 0 1 0 1. What do? What is the control signal that you are going to give? So which are the switches you are going to activate so that, right, you pass on the required data to the output? So this is what is a working, right? You give some input and you want to connect something to the output, means accordingly you need to make the changes in the switches, right? The control signals of the switches needs to be selected in such a way that, right, you pass on the required data. All right. Okay. Now we'll write something related to the crossbar switch itself. The switch requires how many control signals now? We understood that 16 control signals. Control signals, they are SC00 to SC, I think till 33, right? SC33, right? Which means each one of the signal will go to one transistor. Okay, so I have a question now. Is it good? Is this number, we said 16, in the sense in order to perform the shifter operation or for a 4-bit shifter, right, you require 16 control signals to be generated. Now, is it good or bad? So because of that reason, what you can say here is the complexity is very high, right? So now we'll try to modify to get back to our original problem. We try to solve the problem using this technique. Okay, so let's see that. So this means uh, adopt the following changes to reduce the complexity. So the changes what we are expecting are as follows. The first change is this. We try to separate the input and output lines into what is called as a group. We try to make a group. Okay, so 4. How many groups you have? You have to make 4 groups, right? 4 separate groups can be formed corresponding to shifts of 0 bits, 1 bits, 2 bits, or 3 bits. Okay, this is the first thing, right? If you want to have a 0 shift, you make a group. 1 shift, make another group of the switches. Then, right, 2 and 3 shifts are, right, in the same order. Okay, this is the first requirement. Then let's go to the second requirement, right? Switch gates can be coupled together in groups of 4. Always you try to make the group of switches and make 4 such groups, because you have 16 switches, right? So since we have 16 switches, you can always group the switches also into 4 different groups. So this is switch the gates every switch gate, we have how many such gates? We have 16 gates, right? So switch gates can be coupled, can be grouped together. You can group them together in groups of 4. Then the input lines what we have, right, they can also be, right, arranged in two different fashions. Arrange two sets of input lines. Okay, we were drawing the input lines in a in a vertical fashion. You see the previous diagram, right? So this diagram says that you are always drawing that vertically. Okay, but now what I want to do, I want to make two sets of input lines. It will be arranged horizontally as well as vertically, two copies. Okay, right. The input lines are made available both horizontally and vertically. Okay, now let us apply this to build what is called as a barrel shifter. This is the result of this modification, right? So this implies your result is called as, resulting circuit is called as a barrel shifter. Again, now we are going to look at a 4 cross 4 barrel shifter. Okay, let's draw the barrel shifter circuit now. Okay, so as per the requirement, just now we saw that we have to make some modifications and we have to make the groups as well. Okay, this is how the circuit is going to look like now. So I have, let me draw various colors so that we trace input and output separately. Okay, so input lines I'm going to draw using, say, green color. The circuit is pretty complicated. Okay, so it's just a 4 into 4 circuit, but the connections are pretty complicated, right? So I just want to make sure that we don't mess up with the lines that we draw. Okay, so for that reason I'm using colors to distinguish. So the green color is input and the red color is output for me. Okay, right. So same thing needs to be repeated 3 more times. Right, there is a input, this is a input, and I have to write an output below that. Okay, then let's copy this itself once. Okay, now I need the input lines in even in the vertical fashion. Okay, so for that reason I'll draw the input lines like this. Input line, Okay, so these are the four input lines that I'm providing. Now I need to write the transistors between an output line and an input line. Okay, like we did earlier. So this is the output line, and I'm connecting this output line with an input line. Okay, so like this I need to draw 16 different transistors. So number of transistors cannot be reduced. Okay, that's the point here. But still we see that you don't need so many control signals. Okay, after you draw the transistors like this, now you need to make the group of the gates. Okay, let's start drawing the shifting signals now. Right, how the shifting happens you can see. Right, meanwhile you also have to group the incoming signals as well as the gates. We have to make two types of groups now. Okay, the first type of group is like this. That is, simply connect this line to say somewhere here, and then take a point from here, draw this line till here. See, this is how the grouping takes place. Okay, this line is getting connected to this. Now I will connect this particular line to this. Okay, now the same thing will repeat like this. So you start from this point, draw a line till here. Okay, and then make the similar connection. Take a point from here, bring it down, and connect that to this particular transistor's gate. Okay, this is done. Now once again repeat the same process. Take this, draw like this, then take that down and connect this to this. Okay, this is done 3 times now. Okay, this is the step number 1. Then the remaining connections are also to be made in the same fashion. This is first type of grouping. Okay, I'm shorting some of the lines which are supposed to be connected in the following fashion. Okay, now so the shifting signals are provided in the following fashion. They will get connected as per your switching requirement, the shifting requirement. For example, see, the shifting signals will flow in this way. I'll show you this. So it starts from this transistor, goes here. Okay, I'll show like this. This is a shifting signal. See, the grouping of the shifting signal happens in the following fashion. This is what we mentioned earlier. Okay, so this is how you are connecting. Just short it, right? Okay, same way this is going to continue further. There is a connection here. Now repeat the same thing. This will go from here and it will get connected to the next transistor. All right, next start from here, take it to this level and connect it in this fashion. So there is a connection here, there is a connection here, there is a connection here. See, you are making the groups. Okay, this is the next type of group, the blue colored lines. Okay, now you see how the grouping actually happens here. So this is the second thing. I'm starting from here, I'm taking till here and I'm connecting this with this. Okay, so assume that this is how it is getting connected. There is a point here and there is a connection happening here. Now, so this means in the next level this will go further, this will go till here, and you are making the connection between them, that is starting from here to here. So you see that actually you started from here. I'll highlight now. See this, you start from here, it gets connected to this and the last one. See here, all the 4 are connected, right? You start with the first one, it's starting from 1, goes to the second one, goes to third one and goes to fourth one and stops. All the 4 should be connected, every 4 should be connected to form a group. This is what is the requirement. Okay, now you finish this in the same order. You need to finish the complete diagram now. Okay, so that means it's going to take us some time. Okay, so you need to practice this, otherwise there will be mistake. This is important question, repeated several times. Okay, drawing of this particular circuit. Okay, so let's finish this now. So I start from, say, this point, I move around here and I connect from this point to this point. Okay, so this is my connection, this is already connected here. Now I have to finish this starting from this point, going to this point and connecting it. Okay, connect this point to this point. So now you see, let's trace it. Let's do the third one. So I start from here, I go to this, then I connect through black to this, then I connect to this. You see, again 4 are connected, right? And let's finish the last one now. I gave the last one, so this means it has to connect from here Okay, so now just check this. I start from here, I go here and I connect. Okay, then connect this one to this. Now you verify whether all the four are connected in this case. So I start from this, it's connected through black. This second one is connected, third one is connected, and the fourth one is connected. See, you are making the groups. See the see the colors, right? I draw with colors for only that reason, just to trace out what is connected to what. I'll draw. I'll draw. So initial the red, green, initial red, green are fine for you. Is it okay? Initially, you can draw the red and green lines. Okay. Then followed by you can draw the transistors. Okay. Once the transistor is drawn, you start from the first one. Connect this gate with this gate. This continue. Draw that with the next gate. Draw that and connect to the next gate. This is step number one. Okay. Step number two. Yes. Step number two. Connect this. See, change of color. Connect like this and this. Yeah, sure. I'm using the same technique. See, this, 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 and this. And whatever is not, okay, I'll use a different color. Fourth one. So this, this, and the last transistor. See, now every transistor is connected, right, in one or the other way. Okay, now see, the naming has to be done in the following fashion, right? The horizontal lines are the input lines. Horizontal and the vertical green lines are the input lines. So this will be IN3, this is IN2, IN1, IN0. Okay, so vertically same thing. This is IN0, IN1, IN2, IN3. So the connections will be there. So this is a junction. IN0 and IN0 will touch. IN1 will touch with IN1 over here. IN2 touches IN2 here. Other points there are no connections. Okay, so you can see I'm actually highlighting that point. Like this, you highlight. IN3 touches IN3 over here. Okay, then the next naming happens with respect to the output lines. I'll write the output lines on the other side. This is out 3. Okay, so this line is out 2. This red line is out 1, and this is out 0. Okay, now where do you give the shifting signals? Right, shifting signals are easy to give. You can see I'll change the shifting signals naming color, right? This is S0, shift 0. Okay, this is shift number 1, shift number 2, shift number 3. So already you know that it is already connected, correct? So it is connected to different transistors, so you don't have to generate 16 different signals at all. Simply generate 4 different signals for a 4 into 4 shifting operation using a barrel shifter. Okay, so just take some time to analyze this, and if you have doubt, let me know. Okay, the question is like this. The input data is 1001. Okay, and the output data is 0011. Which particular switch you turn on, which particular control signal you are going to give, S0, S1, S2 or S3 is the question. It means I have to make S3 high to get the required answer. Perfect. Okay, then you have this is important question. Okay, so the barrel shifter question has appeared several times throughout your this thing. Okay, let's move on to the next topic, right? That is observations of a design process. Right. So through the experience in the design of this particular shifter, right, as our first subsystem, what are the various observations that we can make is this. Okay. So there could be a question saying that mention the observations on several aspects of design process, up to 6 mark question, right? A common question which appears. All right, so the first point that we observe here is that it is extremely essential to begin by describing the requirements in words, in a sense, so that the whole process results in a very appropriate arithmetic or logic, right? That is the result. So first thing is that you need to describe your requirement very properly. That's the first thing we note. Okay, because if that is not the case, you end up in a 4 into 4, right? The first case, you end up here, which is very complicated, right? But when you explain this very in detail, like these 3 points, then you understood that okay, I can reduce this and I got a right circuit like this. Okay, so this is our first observation. Okay, so that is it is essential it is essential to begin the whole design process by describing the requirements in proper words. Why? It is because so that the process results into appropriate logic, or it can also be an architecture. This is the first observation that we did. Then, if a structure of, say, a standard cell has to be achieved, then the work of that actual detailed design, right, should be kept as simple as possible, or as small circuit as possible. Okay, this is because when you try to simulate only a small functional block, right, it becomes easy for you to understand because one small block is there which you very well know that okay, it is properly designed and it is working fine, right? Then you don't have to go further below one level, further lower level to analyze. Whenever you are fine with one particular block which is already working in a very proper fashion, that's it. You don't have to go further below. Correct? So that's the second point. Okay, so if the structure of a standard cell can be achieved, then work of actual detailed design becomes simple. Okay, simple and small. This is because I know that my simplest block is going to work very fine. I'm very sure of that. Okay, so because of that reason only I'm saying that the complexity reduces, right? So then what happens? Because of this, the simulation, then the simulation of function, simulation of functioning of such cells becomes easy. All right. So this is going to help you in estimating the performance of the complete subsystem. Right. Anyway, I will not write that point. It's understood. Right. Let's go to the third point. Right. Now, once you are fine with the regularity or the generality of your whole system, right? Yeah. It can be exploited to build the structures of any size. For example, I know that how to build a 4 into 4 subsystem, like what we design now, 4 into 4, right? Switch. This means you can definitely extend that to go for a 8 into 8 shifter, correct? Any size you can build. Correct. Once you know that the process of designing like this, you can definitely extend this and write any complicated circuit, any size you can do that. Correct. So that's my next observation. So this is once the regularity and generality generality is achieved. Once this is achieved, it can be exploited to build any other structural size. You can expand that. That's the meaning of this point. Okay, you can expand and get any higher size. Then the next observation is that once the layout of a standard cell is designed, right, it is always possible to calculate the exact area requirement of a subsystem, right? Because I know that once you know one cell structure, the same cells are being repeated later, correct? So you know how many times you are repeating so that you can calculate the total area. So this is the next point. So that is once the the layout of standard cells are designed it is always possible to calculate the area requirements of the subsystems. Okay, so why do you need this? This is because you need to make the floor planning, right? The complete floor planning. That's why this is required. Anyway, that's understood. So I'm not going to write that point here. Then the point number 5 is the process of designing is mostly concerned with the topology of communication rather than the detailed logic, right? So how the communication happens between the subsystems is what is more important than the ultimate derived logic. So the process of communication is more important than the detailed logic design of a system, right? So next we understand that we need to keep the rules, keep the design rules straightforward and simple. We need to choose such design rules only, right? So I think these many points we can always try to understand or observe from the design process we learned so far. Okay, then let's go to the next topic. This is called as regularity. Okay, now let's try to define the regularity, right? The regularity is defined as the it's the ratio of the total transistor count on the chip to the number of transistor circuits required to be designed. for given block. Okay, so the regularity is higher if the whole chip or a large part of the chip can be fabricated with very less amount of standard cells, right? You have to make less design over there because same thing is repeated many times. So if that is the case, regularity is high, right? So this means I can write an equation now. So therefore regularity is equal to the total transistors on the chip divided by the number of transistor circuits to be designed. So this is the denominator. So when you go for a 4 into 4, let us say barrel shifter, right? Right. For example, let's calculate the regularity. This is for example, take a barrel shifter. Barrel shifter 4 cross 4. So what is the regularity of this? Is equal to total number of transistors. You can see 4 into 4. So sorry, not 14, 16, my mistake. So this is 16 divided by how many circuits are there to design? It's only one circuit. So this is 16, right? So if this is high, regularity is high means you can say that it's easy to build that circuit. Okay, whereas when the regularity is low, you have many components to design over there, because as the denominator increases, right, the regularity will reduce. Denominator is going to increase in the sense the number of transistor circuits you have to design is, right, that number is increasing, then only regularity will reduce. So that indicates that, right, the overall the number of circuits you need to design in any chip is more, so less regularity, which means complex design. So overall, that's the idea about this regularity. There have been many questions about regularity. Define and give an example, right? Up to 2 to 4 marks questions, right? You can define, give an equation like this, and give an example. So definition plus equations 2 marks, and example you normally you get a 2 marks. So totally you will get up to 4 mark questions based on this concept.